example 4.1.5b, the transformer described in example 4.1.5 is used to step down the voltage at the load end of a feeder with an impedance of 0.3 plus j 1.6 ohms. The voltage at the input end of the feeder is 2,400 volts. Use the simplified practical transformer model to find the magnitude of the voltage at the secondary terminals of the transformer when the load on the secondary draws 200.8 at a power factor of 0.8 lagging. So I'm going to summarize the givens by drawing a circuit diagram. The first thing we know is that we've got this step-down transformer from the previous example, but we're going to use the simplified practical transformer model. And so we're going to ignore any shunt elements. So that gives us this transformer right here. We've got a series impedance, the primary resistance and primary leakage reactance was 0.72 plus J 0.92. So that's ZP is equal to R1 plus J XL1 there. And then that goes into the primary of our ideal transformer. These terminals here are the primary voltage of the transformer. These terminals here are called VP prime. And then through that we have the primary current. On the secondary of the transformer, we just finished drawing our ideal transformer here. And the output terminals of that are called VS prime. And that flows into the secondary resistance and secondary leakage reactance. That's going to be 7 milliohms plus J 9 milliohms. And then the output of that right there is plus minus Vs, the secondary voltage. So kind of draw a dotted box right there to let you know that all of that circuit represents the transformer. So we've got that filled in. Now we need to go back to the problem and see what else we got. Well, there was a feeder connected to the primary side that has a series impedance of 0.3 plus J1. 0.3 plus J1, so that's Z line. We'll call that for the feeder. Oh, I forgot to label this as Z secondary equals R2 plus JXL2. So there, now it's labeled. So there's our, we've got that. We know that the input voltage to that feeder was 2400 volts. So that's 2400 volts AC, RMS. And then we know that there's a load on the secondary. We weren't told what the load is directly, but we know that it draws 200.8 amps. So we'll just have an unknown load, ZL, and we've got I secondary is equal to 200.8 at a power factor of 0.8 lagging. So those are the givens there for the problem statement. We were asked to determine what the voltage across the load is in this condition. So find the secondary voltage, the output of the transformer. So the technique that we're going to use to solve this, the solution is to refer everything in the secondary circuit across the transformer into the primary using the turns ratio, which this is a 10-to-1 transformer from the previous example. So that we can combine all this into one circuit and get rid of this. That's going to look like this. The solution will be that we've got plus minus 2400 at angle 0. That's the input end. We've got Z line we've got ZP. We've got the secondary reflected to the primary or referred to the primary, that's ZS prime. And then we've got our load impedance, ZL prime. The current flowing in this branch is the primary, and the voltage appearing here is this voltage here, so that's NP over NS times VS prime, and the voltage appearing here, that's this voltage, that's NP over NS VS. So that's the complete circuit model for the reflected impedance there. So all we have to do now is just fill this in. The first is that we need to determine the reflected impedances for both the load and the transformer. So ZS prime is going to be equal to NP divided by NS squared times ZS. So that's 10 squared times 7 milli plus J9 milli is equal to, this is 100 times 1,000, or 7 thousandths plus 9 thousandths, so that's 0.7 plus J 0.9 ohms is the secondary impedance referred to the primary. And then we need to refer the load impedance, ZL prime. Normally we would be able to do this just if we were given an impedance ZL, we could use the same technique. In this case, we weren't given ZL prime. Instead, we were told what the load current is. So we're going to, instead of referring this to here, we're going to substitute in the current. So the current is going to get reflected as the NP over NS is equal to IS over IP. We know IS, it was given to us in the problem statement, so we wanted to determine IP. So that says that IP is equal to IS times NS over NP. So that's equals IS over 10 in this case. So we were told IS is 200.8. And this was a power factor of 0.8. It's a lagging circuit, so that's an angle of negative 36.87 degrees divided by 10. So we just divide that by 10. We get a primary current of 20.08 at an angle of negative 36.87 degrees amps as my secondary current in the transformer, or as the primary current in my transformer. So now we can just use any common technique of circuit analysis to determine what value that we're interested in is. We were asked in this problem statement to determine the output voltage across the transformer's secondary, so we're interested in eventually getting to VS. So the way that pops out to me to solve this, and again, there's multiple approaches to solving many of these problems, but to me I would just take 2400 minus IP times those three impedances in series. So I would say that NP over NS times VS, this quantity here, is equal to 2400 at angle 0 degrees minus IP, the current flowing through those series elements, times the sum of those three, Z line plus Z primary plus Z secondary referred right there. So that's going to give us NP over NS times the secondary voltage, which is equal to 2400 at an angle of 0 degrees minus 20.08 at an angle of negative 36.87 degrees times, we need to start summing all this stuff. The feeder was 0.7 plus J 1.6 plus Z primary, which was 0.72 plus J 0.92, and then ZS prime is the value we calculated right here, plus 0.7 plus J 0.9. So this gives me a NP over NS VS that's going to be equal to 2,328.97 at an angle of negative 0.872 degrees volts. And so to get VS, I just need to divide by the turns ratio, which was 10. So VS equals 2,328.97 at an angle of negative 0.872 degrees volts, div 10. And so that gives me 232.9 at an angle of negative 0.872 degrees volts is my voltage there, right there. So same techniques as reflected impedance in the ideal transformer. You just have to keep track of what you're reflecting, and I highly, highly, highly encourage you to do that by drawing the circuit diagrams. I know it takes an extra minute to do that, and can be a little tedious, but drawing this out really, really will help you keep track of all your numbers and how to refer quantities to the different sides of the circuit to do your solution.